Reynolds. I'm the chair of the Bitterroot Climate Action Group, and thanks for joining us on our first ever Zoom presentation tonight by Phil Higuera. We're going to get started in just a minute. I just wanted to mention a couple of things that are happening right now, even though we're in the midst of a pandemic. Bitterroot Climate Action Group is embarking on an effort to develop a climate resilience plan for Resilie County. We wrote it on this at our last meeting, and we're identifying all the steps we need to go through and the stakeholders and people that will need to be involved. And we're getting a lot of help from the Climate Smart Missoula folks who've been very supportive and recently had the amazing success of having Missoula County and the city of Missoula adopt a countywide plan. Another thing that's happening is that Russ Lawrence is helping us move forward with establishing an electric car charging station in Hamilton. And we're working with the city and the county planner to get this done. And we're probably going to be doing some fundraising before too long for that. So you might watch for that. And the other thing I wanted to mention is that the Climate Action Group is now a federally tax-exempt nonprofit organization, so your donations are now fully tax deductible. So if you want to make a donation, visit our website, which is bitterrootcag.org, and there's a donate page in the menu. We'll be working on getting a PayPal button up there pretty soon. So thanks again for tuning in. This is all being recorded, and we'll make it available on our website. But by being here, you're agreeing to be recorded as well. So now I'm going to turn it over to Kit Tilley, who's chair of our science committee, who will introduce Phil.
Well, I'm really excited to have Phil Higuera here. He was recommended to me as the guy who teaches the Forest Service about fire. And it's been a real pleasure getting to know him a little bit, even if it's all been over computer screens and by email. Today, he's going to talk about wildfire and climate change in the West. And he is a professor at the University of Montana in the Department of, in fire ecology, and he teaches PaleoEcology, directs the PaleoEcology and fire ecology lab. And he does research by hiking or flying into mountain lakes and looking at layers of ash that are under the lakes, and it sounds like amazing research and a really good way to look at historical wildfire. And not only that, but he just got back from a 2-week bike trip where he went on the Elk City Road and then went all the way on to Haley, Idaho. And it's kind of an impressive trip, it sounded like to me. And pretty exciting vacation. But anyway, without any further ado, let's let him tell us about wildfire and fire and climate change in the West. And he'll give us a little background on how Zoom will work and how you can ask questions and that kind of thing. Okay, Phil?
All right. Thank you very much, Kit. And thanks, Kit, for the invitation. Thanks, Peter. When Kit sent this invitation, it was just pre-COVID, but nonetheless, I was excited to be able to interact with your group. Sounds like you guys are doing a lot of interesting things, and just from the announcements that Peter just made, it's clear that you guys you're tapped into the right things already. So I'm excited to be able to make this work despite not being able to all be in the same room. And for those of you who haven't used Zoom before, most of you are muted, and we might mute you if you come off of mute in the talk. And then during the talk, if you experience any issues with connectivity, the first thing to do is to turn off your video. So during the talk, if you can turn off your video, you should be able to hear and see any slide transitions better. There is a chat feature in Zoom that you should see by hovering over probably the bottom of your screen. And that's a good place with this many folks. It's a good place to put questions. I'll have my eye on that during the talk, so if there are questions, I'll aim to answer them in there. And then at the end, we can start with questions from that list, and eventually we can open it up and we can unmute and everybody see each other on video. And I'm hoping we can have a good conversation at the end of this. So big picture, fire and climate change it's a huge topic. We all live in an area where we're quite familiar with experiencing and living with wildfire. The photo that you should be looking at here is the Lolo Peak fire, of course, from 2017, a couple of years ago. So we're all well familiar with this. What I'm going to do in my talk tonight is just kind of dip into four topics about fire and climate change. I'm going to start with a little bit of motivation, and then I'll introduce those questions. I just want to say up front that this is going to be a small dip across these four questions, and my intention here is to leave there are going to be plenty of questions that you should have that we can discuss at the end of this. So with that, I'm just going to start with some background information. Some of this I suspect many of you know, but this is basically the motivation for why understanding fire and climate change is important, not only to people like you and communities like the Bitterroot and Missoula, but this is a topic that is increasingly important across the US and across the globe. So it's only getting more and more important. In part, that's because of this increase in area burned that we've seen across, this is the lower 48 here, so area burned in wildfires across the lower 48 since 1984 to 2017. And you can slice and dice this different ways, but different regions. But in many regions, you're seeing this increase in area burned over the past several decades. In the Northern Rockies, if we did slice and dice it by the Northern Rockies, what we would see is that a lot of that increase is occurring in our neck of the woods in the Northern Rockies. Another statistic that is pretty striking here, directly related with more area burned per year, is basically having more days per year to burn. So the length of the fire season has increased significantly over the last several decades. It's almost tripled. This ends at 2012, so it may have tripled by this point, but fire seasons are getting much longer. And in short, referencing to the 70s or even the 80s now is not really useful for what we're experiencing. Of course, with this increase in area burned every year, it also comes with a lot of other costs. This figure on the right here, the black line is area burned across all the US federal lands. And so this includes Alaska as well. So you see this increase from the mid 80s that we saw earlier. And the blue line here is annual suppression costs in billions of US dollars. So we see there's a pretty tight correlation between area burned and how much money we're spending on fire suppression, which it's safe to say that's the main way that we respond to fire activity. And many are also probably well aware that the increase in suppression costs for agencies like the Forest Service, highlighted here on the left, that's coming at the expense of all the other responsibilities that these agencies have. So in the Forest Service, over 50% of their budget, this is 2014, over 50% of their budget is spent on fire suppression. This just says fire management, but the bulk of that is fire suppression. There's some some changes that have happened in the last couple of years that will hopefully ameliorate this. But the bottom line is that our relationship with fire right now, the way we're doing it, is pretty costly. That's just in dollars. And then, of course, the greatest cost is when wildfires take human lives, whether they're firefighters themselves or residents. So particularly over the last couple of years, 2017, 2018, and then, if we go across the globe, 2019 and 2020 in Australia, wildfires are increasingly becoming human disasters. So increasingly, wildfires are interacting with our built environment and are having deadly consequences. So that's some of the big picture motivation for why this topic is so relevant these days. And I would say even in light of the pandemic, we'll see how this fire season shapes out. Fire is always something that pops up to the top of the news somewhere in the world. So I always like to start with a reminder, despite those important statistics and the important trends, and despite how it can feel like we're living in these unprecedented times, it's a good reminder to us that fire itself is not necessarily the problem. Fire, if we go back in Earth's history, it's a long-standing natural process. It's been on our planet for 420 million years. Basically, as soon as there were plants on land and enough oxygen in the atmosphere to sustain combustion, there's been what we call wildfire. And likewise, humans, we've evolved with fire and have really used this as an effective tool to help us live. So we've used fire domestically for 400,000 years, and we've used fire to modify and essentially manage our landscapes for about 50,000 years. So there are a lot of other examples of how we have related with wildfire in the past that differ from the way we relate to it and the experiences we have with it now. So fire itself isn't necessarily the problem. And ultimately, we need to figure out how we can live with wildfire because it is this natural phenomenon that's not going to disappear. So in the talk today, I'm going to dip into these 4 questions. The first one, I just laid out some patterns, and I started with this increase in wildfire activity. Of course, anytime we have a regional fire year around here, the first question that journalists and the public want to know is why is this happening? So I'm going to dip into the science a little bit about what are some of the key drivers of these recent increases in fire activity. Talk a little bit about what the ecological impacts of fire and recent fire activity, the ecological impacts of fire in the past and in the present. And then a little bit about what we can expect in the future, given ongoing and projected climate change. And then this was a good transition into discussion, some of the what can we do given the answers to the first 3 questions. So to start off, what explains this recent increase in fire activity? Lots of discussions have occurred and could occur about looking at those time series and coming up with narratives. I'd say prior to about 15 to 20 years ago, I'd say the overarching importance of climate as a driver of fire activity was really poorly understood in the fire science community. So over the last 20 years, we've learned more and more about how widespread fire activity, and what I might use this term throughout here, regional fire years. When I say that, think about something like 2017. There are years where there's many large fires across a region like the Northern Rockies. There are piles of papers that support this statement that widespread forest fire activity is strongly linked to seasonally warm, dry conditions. And this is true across multiple timescales. So and what I mean by that is it's true when we look at data sets over the past 30 years. It's true when we look at data sets that span the last 100 or 120 years, going back to the early 1900s, including the 1910 fire. It's true when we use tree ring records to go back several hundred years, 300 to 500 years. And we also see this when we use lake sediment records and look at these relationships over thousands of years. So this is it's meant to be purposefully overwhelming here. These are just a handful of papers that are highlighting climate as a key driver of annual area burned, most of those across the West. So climate change is climate, and therefore climate change is a critical component of what determines fire activity. This does not mean that humans and vegetation are not important, right? Most fire ecology classes and fire behavior classes focus a lot on the importance of fuels for driving fire behavior. And this work doesn't mean that fuels aren't important. Fuels are very important, but at different scales, often at smaller spatial scales and sometimes at smaller time scales. So this is what this relationship between climate and fire activity looks like. This is one of the simplest graphics, I think, that displays this relationship between climate and fire activity. This came out a couple of years ago, 2016. So the x-axis looks a little bit funky at first, but what this is measuring, fuel aridity, it's basically all the ways in which temperature and precipitation ultimately affect how dry fuels are. So we've all seen Smokey Bear and him pointing, to low, moderate, high, or extreme fire danger around our communities. That's ultimately what this reflects. And values over here on the right are very dry fuels, high aridity, and on the left are wetter fuels. And then on the y-axis, this is area burned in forests in the lower 48 in the green in this little map here. And this is showing annual area burned from 1984 to 2015. So it's similar to the first graph we started with, but it's showing the relationship, the correlation between fuel aridity and total area burned in a year. And you can see this strong positive relationship. In ecology, this statistic right here is a very high statistic. It basically means 3/4 or 75% of the variability in how much area burns from year to year can be explained with this fuel aridity metric alone. So it's really quite astounding. And again, it's important to know that this is at this large scale, right? So we don't need to know much about the specific fuel conditions or even topography at these large scales. When we have unusually warm, dry summers, we get more area burned. And of course, like when I talk to my mom and I tell her that, she's like, duh. And that's often an important first reaction, but it's also good to be able to document this stuff. And then the other thing in this figure, these red dots, this is the 21st century. So you can kind of see that increase in area burn that we were looking at in that first time series. So the red dots are 2000 to 2015, and you can see that they're starting to pile up here in the upper right of the figure. So there's a strong relationship between fuel aridity and total area burned. And in the 21st century, we're seeing more years up here with high fuel aridity and therefore high area burned. So climate's a key driver of annual area burned. Lots of studies support that statement. A really important additional piece that came out in the literature again in 2016, this is actually the same paper, we're starting to be able to attribute the degree to which human-caused climate change is adding to this increase in area burned. So logically, if climate warming is directly related to more area burned, and based on IPCC reports, or based on the preponderance of the scientific community, humans are increasing the Earth's temperatures. Logically, there'd be some amount of that increase in fire activity that's due to human-caused climate change. And that's what this study teases out. So human-caused climate change is a significant driver of this recent increase in fire activity. And without going too much in the details in this graph here, this is just showing the take home from this is about 50% of that increase in area burn that we see over the last several decades, it can be attributed to human-caused climate change. So this red line is the total area burned over that period observed, and then this black line is what we would have expected to happen if we didn't have human-caused climate change. And you can see the black line's about half as high as the red line. So this is an important addition to our understanding of fire and changing fire activity. And ultimately, it kind of makes things more complicated for us for a number of reasons. Okay, my screen just went through a little thing. Kit, can you give me a thumbs up if you still see the slide? Okay, good. And if I might need to restart the program here. Of course, this happens at the wrong time. Yeah, let me restart this for a second. This would be a great time if you guys have any questions to put into the chat. Okay, I'm almost back. Okay, can you give me a thumbs up again if you see a slide? Okay, great. We should be where we left off. Okay, so human-caused climate change is a significant driver of recent fire activity. Then on top of this, we have, all the land uses that have occurred over the last century. And again, I suspect that you guys are well familiar with this. The take home here is that past land use patterns, forest management, fire suppression included, exacerbates these climate-driven increases in fire activity. Fire suppression certainly has removed a critical ecosystem service from many forests. The resulting accumulation of fuels increases the likelihood of high severity fires. A really important addition to this, though, which I think is underappreciated in the public and in the scientific community sometimes, that this is really specific to low elevation forests. This statement doesn't apply everywhere. So it really applies to low and mid elevation forests. And then, of course, increased human infrastructure is in part what's leading to this increase in wildfire disasters. We're living closer to flammable landscapes. So not only are these landscapes are burning more often, but we're living closer to these landscapes that tend to burn. We all know that humans start fires. Smokey Bear's done an excellent job ingraining that in our heads. So humans start the majority of fires in most regions by numbers. And this is increasing with human populations. But this is an important addition to this. Across most of the West, with the exception of the Mediterranean, California. So in particular where we are, see these blue values are low percentage of human ignitions. Across most of the West, the majority of area burned comes from lightning ignited fires. And in the Northern Rockies where we are, that's about 2/3. So around 70% of the area burned still comes from lightning ignited fires. So even if we took away all human ignitions, we would still have quite a bit of burning. And then humans, we also try very hard and do a really good job of putting out fires. Right? This is basically our tactic that we have taken for the last 100 or so years. So 98% of the fires that start are suppressed with initial or secondary attack efforts. And only 2% escape and become large fires. So this looks, and this has largely been the metric through which we've measured success in fire management. We're doing a great job, quote, quote. We are putting out 98% of the fires. But again, the difference between number of fires and area burned, the majority of area burned, 95% of the area burned, comes from the 2% of fires that escape initial or secondary attack. So most of the area that burns out on the landscape occurs in years like 2017, where we have large fires are technically classified as large or mega fires. And then likewise, those are the fires that cost the most money. So these 2% of fires that escape initial or secondary attack, they also account for 85% of the dollars that we spend on fire suppression efforts. Okay, so that's a little bit in terms of why fire activity is increasing. Yeah, I see in the comments here another land problem is logging that's removed large fire resilient trees and replaced them with dense young stands, which are much less resilient. Yes, logging and past land use is an important component that determines fire behavior in many regions. Again, as we go down in spatial scale, the more important that past land use history becomes. So next I'm going to transition and talk a little bit about what are some of the ecological impacts then of wildfire in general, and then the wildfire in this era of increasing fire activity. So when we enter into this conversation, and this is the conversation that also happens anytime when fires are burning in our backyard. The other thing that the media want to know is, is this normal? What's going to happen? And answering those questions is really contingent upon what specific ecosystem we're talking about. So fire ecologists, we have this concept of a fire regime. And this is the way that we organize what's a really complex process. So we use that one word fire, and it kind of implies that all fire is the same. But just like life is extremely diverse, fire is extremely diverse. The way it burns, the frequency at which it burns, how often it typically occurs at a point in the landscape, and then the impacts that it has on the organisms in the landscape. Those all vary significantly across different ecosystems. So we can't give a single answer. So this concept of a fire regime is the way that we summarize that. And the photos here are just contrasting what would be a normal, or what we'd expect, the type of fire we'd expect in some place like Yellowstone National Park in a subalpine forest, a really scary to humans crown fire that's going to kill most of the trees. And then on the right here, this is a little friendly creeping surface fire in Ponderosa pine stand. Right, both of those are fire, but these are two very different fire regimes. So when we talk about ecosystem impacts, they need to be assessed within the context of the historical fire regime in a system. And really, the reason that's important, it's not because we're trying to get back to some condition in the past, but the reason that historical fire regime, or one reason that historical fire regime is important, is because that tells us what the organisms in that system have evolved with. And ultimately, that's going to determine a lot of the traits that they have that allow them to either survive fire or regenerate after fire. Ultimately, it's what allows them to exist in an environment that has experienced fire for thousands of years. So broadly, many ecosystems have been resilient to wildfire. And resilience is it's a catchy term now, and I was used in the introduction already, so I know you guys are somewhat familiar with it. I'm going to give you an ecological definition in a couple slides, but in a nutshell, we mean the ability for a system to bounce back after a disturbance. Yellowstone is a good example here. This is an aerial, or this is a satellite image, so you can see the scale that we're looking at here. This is Yellowstone Lake. And the 1988 fires, you can see the burn scar here in this satellite image. In 2008, you can still see some recovery happening, but in many of these areas, forests regenerated as they have done for thousands of years through serotinous cones of lodgepole pine opening up and those trees regenerating. So a lot of places we look across the landscape today and in recent decades, we see plenty of evidence of ecosystems being resilient to fire. And in a nutshell, that is in contrast with the kind of the knee-jerk reaction of fire being a disaster or an ecological disaster whenever it occurs. When we look back further in time, Kit mentioned a little bit of a lot of my work is based on using lake sediment records and reconstructing fire history over thousands of years. This is the one slide I have of this stuff in the talk. We can talk about this more if you're interested, but we collect the mud basically at the bottom of a lake in these cores. We slice them up in the lab in really fine intervals, centimeter. And then in each one of those sections, we can look at different things like charcoal, pollen. We use radiocarbon dating to know the age. Excuse me. And we can reconstruct fire history over thousands of years. And so when we do that, in many, many cases, so this is a record going back a little over 4,000 years. And the red lines here are when we've reconstructed high severity fires. And those blue lines are lower severity fires. They didn't kill all the trees. And these are just two proxies. It doesn't really matter what they are. They're components. They're telling us something about the soil properties in the ecosystem, nitrogen and carbon. And what we see when we look at multiple proxies and when we look at the pollen, we see plenty of evidence that these forest ecosystems have been able to bounce back from wildfires in the past again and again and again. So that's perhaps, that perspective to me gives me some hope that maybe ecosystems are a little bit tougher than we think. However, it seems like with each passing year, we're putting systems to the test more and more, and increasingly we're seeing examples of where what ecosystems are experiencing today is literally unprecedented, even on these long time scales. So it leads to this question. Hopefully my slide changes again. Okay, that changed and I'm back. Oh, and I see the yellow line down here. That shouldn't be there. Erase all ink. Well, I'm going to go with that. I don't know what the yellow line is doing down there, but sorry about that yellow line if you see that. So with ongoing climate change and increasing wildfire activity, it's increasingly raising this question, whether ecosystems will remain resilient to fire activity in the face of changing climate. And to go back one slide here, this is our ecological definition of resilience. And in the science of ecology, it's something that we can actually measure. Still a little bit squishy, but it has a measurement to it. It's the capacity of a system to absorb a disturbance and reorganize while undergoing change and still retain the same structure and function and feedbacks. And maybe you've seen these ball and cup diagrams before, but we love using these to represent resilience. What this is illustrating is an ecosystem. You can think of your favorite forest ecosystem where you like to go hiking. It's represented by this ball. We know that ecosystems are not static over time. They change continually. And so that would be represented by this ball bouncing around in here. And maybe a wildfire changes it quite a bit. But like in the case of Yellowstone, it will bounce up here, but it'll come back to where it started. So this is the conditions under the historical range of variability. You can think of that as that variability that we just looked at in that couple thousand year lake sediment record. What we're concerned with climate change is that this basin here is becoming much shallower. So climate warming is making it easier for this system to move over a threshold and end up in a different state. So here we just say state 1, state 2, this could be a forest, or in state 2 could be a non-forest, or a forest with completely different tree species. So what ecologists and scientists are focused on a lot right now is understanding if, where, when, and why this is happening. So it's something that we expect through the combination of climate change and increasing fire activity. Okay, so looking forward, what are some of the things that we can expect in the future? So first off, evidence strongly suggests more fire in our future, primarily because of the kind of convergence of climate projections for mid-century and late century. And this is just one example. This is across the West. And the red colors here, this is basically aridity. So high values are very dry. Blue values are wetter. And if you look up in our neck of the woods, and like much of the West, we see mostly red values. If we use these future climate projections in combination with those strong statistical relationships between climate and annual area burn that we looked at in the beginning. Oops, I'm going to go back to that. If we pair those two, the conclusion that leads to is that we're going to expect more years with conditions that are suitable for widespread burning. So just like we saw those years piling up in the upper right of that graph in the 21st century, we expect that trend to continue. So this is a little bit of a cop-out because saying, we don't know exactly what's going to happen, but we do know that we're going to have more years with conditions like 2017. That's going to happen more frequently, and most likely it's going to lead to more area burned over time. In this figure, this is showing area burned in the greater Yellowstone ecosystem. And this is the past up through, I think, early 2000s. And this is a particularly provocative projection. This is from almost 10 years ago now, 2011. But what this suggests is that by the second half of this century, summers in the greater Yellowstone ecosystem are going to be similar to 1988-like conditions almost every year. Of course, that most likely won't translate into 88-like fires every year because we're going to run out of fuel at some point. But fire, the suitability for fire is going to be increasing. And then I'll go back one here, and I'll just point out that the best source for information on climate change in Montana specifically is this Montana Climate Assessment. And this gives some numbers now to the redness that we saw in that graph of Western North America. So in Montana, temperatures are projected to increase under all climate scenarios and emission scenarios. We can talk about that later if we need to. Between 4.5 and 6 degrees Fahrenheit by mid-century, and up to 9.8 degrees Fahrenheit by the end of the century. Precipitation projections are inherently more tricky, but precipitation is generally expected to decrease in the summer. It might increase in the winter. With warming temperatures, a lot of that will not come as snow as it did in the past. It will come as rain. But together, these two are what lead to those projections of warmer, drier summers, basically higher fuel aridity. That higher fuel aridity, of course, makes it easier to burn. That warmer, drier condition also makes it harder for trees to establish. So I'm going to talk about that here for a minute. So the combination of increasing fire activity and climate change is going to change. It's going to change our landscapes. Warm, dry climate conditions are expected to reduce post-fire tree regeneration. So that resilience that we saw in the past is going to be increasingly compromised or challenged. We expect this to occur first near lower tree line, which is where conditions are already, where trees are already growing near their warm, dry edge of their distribution. So this is a study that came out last year led by a postdoc working with myself and colleagues at Kim Davis. This includes some sites in the Bitterroot and a lot of sites in the Northern Rockies. And what this is showing is this, when we study and understand how tree seedlings respond to climate, we see these distinct thresholds. So the y-axis here, this is the likelihood of a tree regenerating after a wildfire, recruitment. And the x-axis is the surface temperature, maximum surface temperature. This is what the seedling experiences. And once you get above about 48, 49 degrees Celsius here, it's pretty warm, there's a distinct drop in the probability of recruitment. So these thresholds are going to increasingly be crossed in the future, and that our expectation then is that in many areas where fires are kill all the trees, we might not expect to see trees come back. And in the warmest and driest areas, we wouldn't even be able to go out there and plant trees simply because the climate conditions that facilitated the adults that were killed there no longer exist. So big picture, this requires some challenges in terms of identifying areas of the landscape where trees will come back naturally, where trees could come back if planted, and where it's a waste of our resources or time to even attempt to have trees come back because climate conditions are unsuitable. I'm going to skip that and then move to this what can we do part. So big picture, the bottom line is we need to plan for more wildfire. And this is an important paper that came out a couple of years ago representing a host of fire scientists emphasizing this point. And there are a couple of things that were pointed to in this paper. Looking forward, we can't, it's unrealistic. It's just not, it's unrealistic to think that we could do something to remove fire from the landscape. It'd be similar to saying we're just going to stop all earthquakes and stop volcanic eruptions. And looking forward, it's important to recognize that fire is going to be the dominant treatment on federally managed forests. And what I mean by treatment there is it's the dominant thing that's going to happen to the landscape. So forest managers think about a fuels treatment or timber activity as changing habitat. No matter what we do, the dominant treatment is going to be the impacts of wildfire. And that's shown here in this graph. The red line is area burned in the Northern Rockies. The green line here is area harvested for timber harvest. And many of you are probably familiar with the late 80s, the heyday of timber harvesting in this region. that's right here, you know. So even if we were harvesting at the levels that we were in the late 80s, this is how much area we would be affecting each year. And these recent large fire years are just orders of magnitude more. So it's a problem we can't ignore. It's not going to go away. Many of you are probably familiar with fuels treatments. Fuels treatments, they're a really effective way to modify fire behavior. They're very important locally, particularly around communities, because they allow firefighters to protect structures and humans more safely and more successfully. But also because of the scale at which fire operates across the West, fuel treatments are not a reasonable way to alter these trends in fire activity that we started with. So we couldn't implement fuel treatment across the entire West and change this increase in fire activity, or it's very unlikely. And here, this is showing the orange bars. This is area burned from 2004 up to 2013. And the black areas here, these are fuels treatments that were put in during that time period and then subsequently burned. So again, the main point here is that there's order of magnitude difference between the areas affected by wildfires and the area of fuels treatments that we've put in that have then been used or tested by wildfire. And even if we could somehow, you know, increase these black bars to somewhere up here, you know, fuel grows, vegetation grows. So basically by the time you complete this, you're going to have to start over. And it's a really expensive proposition. So I'm going to skip that. Then last year, a group of scientists, including some folks, myself, and the next thing that we're kind of pointing out here is that even this concept of resilience to wildfire, we might need to start to reconsider exactly what that means as conditions change more and more from what we've experienced in the past. And what we mean there is typically when we're talking about resilience, we're thinking about what we call basic resilience, which is bouncing back after a disturbance. So this, you know, rebuilding infrastructure after a fire event is a great example of basic resilience. Trees regenerating after a wildfire is a great example of basic resilience. I've got a couple on here as well. The next type of resilience that we're starting to discuss and starting to be discussed in the community is adaptive resilience. And this emphasizes the need for adaptation, and it also emphasizes kind of the expectation that where we're going may not be like where we came from. So the goal is not necessarily to get back to where you were, and you might accept some changes in an ecosystem for other goals. So fuels treatments and prescribed fire to lower fire hazard in strategic locations, regardless of whether that's what the forest was like 50 years ago or 100 years ago. Another interesting adaptive resilience strategy that PG&E employed last year was to shut down power lines during periods of high fire danger. That came at significant costs for their users, and significantly the impacts were not equally distributed. Then this last type of resilience here, transformative resilience, this is basically looking forward and recognizing that in some situations, the whole way that we operate is going to have to transform. An example is moving from having an air filter in our own house to having smoke filtering HVAC systems become the norm for all public facilities, public schools, public libraries, etc. So that's a big scale change. And then to link back to the shutting down the power line during high fire danger, the way that would look with transformative resilience would be to kind of address the problem itself, decentralize the power grid, or bury power lines to reduce the vulnerability to high wind events and high fire danger. So each one of these types of resilience are going to be, each one of these is going to be relevant in different situations. So there could be a lot of places in the Bitterroot where we could go, and we may still expect to be able to maintain basic resilience. But there are other places where we're going to have to think about and call upon adaptive resilience. And increasingly, as climate change pushes us forward, increasingly we're going to need to have to think about transformative resilience. Okay, I'm going to skip that. Last two slides here. That's big picture stuff. I want to bring it down to what you can do as community members, and maybe you guys let me know if you know about this already in the Q&A. But there are increasingly excellent community efforts to build the relationships, share the knowledge, and do both pre-fire planning, during fire planning, and what they call post-fire, but what we like to call between-fire planning for community members. So this Fire Adapted Communities Learning Network is a great resource. On the left here, this is the general program. They have programs all across the country. Montana has a program that's on the right there. And this little map is showing groups that have joined across Montana, and just point out that Ravalli County is absent from that. So that would be one great thing to have happen, to have Ravalli County or some groups in Ravalli County join this Fire Adapted Communities Learning Network. And I think if you guys are looped in with Climate Smart Missoula, they are probably looped in on this in Missoula. So these are just resources from there. I'm not going to go into those, and I'll end with the hopes of being able to have a little bit of discussion. So to wrap up, why is fire activity increasing? Natural and anthropogenic climate change is a significant driver of increasing fire activity. Human activity, including past management and human ignitions, are also important, but certainly a main driver is increasingly fire-conducive climate conditions. What are some of the ecological impacts? We have resilience in a lot of ecosystems, so every fire is not a disaster. However, as we push the envelope more and more, resilience is increasingly being compromised in some ecosystems. And the challenge for us is to understand where this is happening, both now and where it will happen in the future. What can we expect for the future? Climate projections kind of overwhelmingly point to summers that are more conducive to widespread fire activity throughout the 21st century. So we do expect our interactions with wildfire to increase. And with that increasing fire activity in combination with climate change, we expect fire to accelerate changes in vegetation and maybe changes in social communities as well that would otherwise take longer to occur. Ecologically, this is going to happen quickest or first at the warm, dry edge of species distributions. And then what can we do? Need to recognize that fire it's here to stay. It's going to be the dominant thing that affects our landscapes, particularly public lands. And we need to plan for it. We can't, no longer can we be surprised by these large fire years like 2017. And then I think the nitty-gritty is starting to prioritize actions among these three different types of resilience categories: basic, adaptive, and transformative, knowing where each one of these will be most efficient. So with that, I'll leave that up there, and hopefully we have some time for questions, although I see we're approaching the top of the hour. So just a reminder, you should be able to see unmute if you want to unmute and ask a question. And I think there are two questions in the chat that I'll speak to if people are thinking about questions. So, Forest Service likes to say that they can only affect the amount of fuel, but you suggest that fuel moisture is more important. And they can certainly influence that, for example, by avoiding logging, which opens up the canopy and will dry out fuels. Yes, when we look at the fire triangle, fuels, weather, and topography, classic fire management emphasizes that the one thing that humans can affect most is fuel. We can remove fuel, and then we unintentionally affect the ignitions part, but pretend we remove that. I think one of the implications of climate change is that that side of this fire triangle we can't affect on a small scale, and what that implies is that we're not going to be able to use fuels treatments to get ourselves out of this challenge entirely. See, unlike California, most fires here are lightning caused. Yep. Yeah, so around 2/3 of the area burned here is by lightning fires, not power line caused. So why would you shut down? Yeah, the shutdown power grids would not be relevant here broadly. Could be relevant in a small scale situation. Is there an estimated rate at which the forest is maybe moving up in elevation? Oh, that's an awesome question, and a classic question in ecology is how fast does tree line move uphill? I don't have an estimated rate locally, but what I could say is that if we look at changes in tree line over the last 100 years or so, the distances that we're talking about in many regions are tens of meters. So 30, 60, maybe 100 or 200 or a couple hundred feet. So not super fast. One of the reasons that fire is important is because fire can speed that up. So that's talking about upper tree line, trees moving up. The thing that fire can do to accelerate that change at lower tree line is by killing trees. And then if trees don't regenerate, all of a sudden that shift in tree line is much quicker than would happen in the absence of fire, because those mature trees could live for many more decades under warmer, drier conditions. Do we expect more wind events with more stressed tree falls? Patty, I don't understand the second part. Do we expect more wind events with more stressed tree falls? I'm not getting the link between the wind events and tree falls, because I think at first I'm thinking about, are you asking about wind and like increase in wind in terms of driving fire activity, or are you thinking more smaller scale, like winds where there's been tree fall? I don't know if you can unmute, or as trees dry, are they more likely to fall? Not necessarily at the scale that we've been talking about with fuel aridity. So low or high fuel aridity doesn't necessarily make them more likely to fall. But if those drought conditions exist for longer, the other way that trees can and are being killed are simply by drought. So not so much up here, but in areas in the Southwest and in California, there's widespread tree mortality from drought itself. And yeah, certainly along that continuum, as the tree's dying, it would be more likely to fall. The Montana Climate Assessment, yeah, it came out in 2017, but of course reflected work over the previous several years. The question is there, do you know if there's any effort to update it? Right now, I'm participating in part in that group, and what they're doing is they're still translating the climate change projections to what it means for specific stakeholders, so what it means for agriculture, what it means for health. I suspect, given funding, that they will update it typically, like the IPCC, those updates are done every, I'd say, like 4 to 7 years. So I don't know the specific timeline for the Montana climate assessment, though. Next question, is there an advantage to create more water storage in the high country? In terms of lowering, I mean, there could be an advantage for more water storage in the high country in terms of providing water for agriculture or human use lower down. And just from a pure water resources perspective, that would be one mechanism to help address the lack of water that we're going to see because of the lack of snow in winter. So as more precipitation falls and rain in the winter, that's going to go into runoff instead of being stored as snowpack. And it's harder to capture that except when you have reservoirs out there. I don't know that it would have an advantage in terms of keeping fuel moisture higher necessarily. So I don't know that more water storage in the high country would necessarily affect the susceptibility to fire. In climate change and human health, addition to the Montana climate assessment will be out in late summer. Awesome, Rob, thank you. Yeah, that's a good resource for folks to know about. Yeah, some people argue that we need to log to create early seral habitat. It looks like we can expect fire to accomplish that without our help. Yeah, I mean, depending on why. So some people argue that we need to log to create early seral habitat and then ... for what? Oftentimes early seral habitat is justified or is motivated by wildlife management needs or desires or goals. So early seral habitat can be more attractive to wildlife. But yeah, big picture, I think there's going to be plenty of early seral habitat around due to fire alone without our help necessarily. I think that's fair. Does the DNRC have a staff that is assigned the job of leading adaptation planning with the counties? I squarely do not know the answer to that question. Well, the questions are trailing off, so. And nobody's been brave enough to unmute.
I tried to send one. This is Jill. Can you hear me?
Okay. Yes, I can.
I couldn't get it to send, but I wanted to know the effect of climate change on the pests and diseases in the forest.
Mm-hmm. In some ways, broadly, it's similar, both in that, you know, pests and diseases, let's take mountain pine beetle. In some ways, it's similar to fire in that large outbreaks of mountain pine beetle are something that those trees and forests have evolved with for thousands of years. So on the one hand, it's something that is a natural process that's part of those systems. But also, like fire, climate warming is exacerbating that disturbance. It's making it occur more frequently, and it's making it occur at higher elevations than it had before in the past. And we're pretty sure that it's occurring over broader areas than have occurred in the past, although we don't have good reconstructions of past mountain pine beetle outbreaks, for example. But warmer winters in particular allow insects like mountain pine beetles they have better survival. And then, you know, I showed longer fire seasons. That basically means it's warmer for longer. From the perspective of insects like a mountain pine beetle, that also means that they can have 2 life cycles in a summer, for example, whereas in the past they may only have had 1 because the warm season was shorter.
This is Kate Fulton. I have a question. Can you hear me?
Yes, I can, Kate.
Well, first of all, my comment is that on the screen, it's hard to see what's on the right side because the people's pictures are there. So they've covered up some of the information on the right side of your graphs. And so
There we go.
the question I have is in terms of that copy or the Montana Fire Adapted Communities chart or graph or whatever it was. I couldn't read it at all. Can we? Is there a way to get a copy of that?
Yeah. Is this what you're referring to?
No, it was a listing of places in Montana.
Oh,
I think
yeah.
it said.
Yep. Here. Yes. And I provided this link right here. And what I can do is I can provide these slides in addition to the recording. The recording is useful, but it's really hard to go through and find
That'd
things.
be
So I can
great.
provide these slides. And I've purposely put some links down here so that you guys can follow that. So
Which links are you talking about? Oh, I see.
Yeah, at the bottom there, that's the web address for.
Fire Adapted Network.
Yep.
Okay, thank you.
And both of these graphics are from that page.
Okay, thank you.
Mm-hmm.
I have a question. This is Gail Goheen.
Mm-hmm.
My question is, the Forest Service has planned and is continuing to plan some massive logging projects in the Bitterroot Valley, supposedly to reduce fire hazards. Are these likely to decrease or increase fire danger, especially if old trees are logged?
Generally, so there's a couple of things you'd want to look for in forest management action that was proposed with the goal of reducing fire hazard. You definitely want to make sure that there's some prescribed fire included in that to clean up to consume the fine fuels that are left over after many tree removal management actions. So if they don't have plans to include prescribed burning to clean that up, that's one inconsistency with that goal of reducing fire hazard. The other thing to look for is if they need to be upfront about what their goals are. If they are proposing to do tree removal for forest restoration and you're in high elevation lodgepole pine stands, that's inconsistent. And often what I challenge people to just say, we're just doing this to reduce fire hazard, and we know we're changing the system. If you're removing trees in a high elevation forests that have historically experienced high severity fire, it's okay if your goal is to just reduce fire hazard, but that needs to be upfront. You asked about removing large trees. Removing large trees would take that system away from what it was like in the past, depending on the elevation. So that would be inconsistent with maybe some forest restoration goals. But big picture, sometimes I say this jokingly, if you want to reduce or eliminate fire hazard, right, then yeah, you remove all the vegetation and you pave the place. That's a little bit ridiculous, but the point is, it should force you to have to be upfront about what your goals are and the values that you're supporting in a management plan. Any other questions? It's crickets.
if there aren't very many, if there aren't other questions, maybe you could mention where people could communicate with you by email. And
Yes, that's a good suggestion, Kit. I don't think I have that on my.
on your first slide, maybe?
Yeah, I'll go to my title slide here. And now, given that question, you guys may have been looking at the different screen the whole time. But there's my email. philip.higuera@umontana.edu. And if you just Google that, you'll find my University of Montana profile. Yeah, I'm happy to answer additional questions and or point you in the direction of folks who can answer the questions better than I can if I can't answer it. So yeah, I hope you guys learned something. I enjoyed the question and answers, and I think the work that you guys are doing is really important, and certainly under the large umbrella of climate change, fire in this region is right up there as a major issue that we need to wrestle with. So I appreciate that you guys are all interested in that and working to help tackle that.
Okay, well, I'd like to go ahead and thank Phil for being willing to give us a talk in this format, and thank all the participants, especially those who asked questions. And I think we're ready to say goodbye for the evening.